Hey everybody, it's Mr. N, and we are going to do the linear approximation lesson today.
This is 310 in Stewart 9th edition and 39 in the 6th edition.
Okay, so let's talk about what linear approximation is. Let me first read this off to you right here. If a function f is differentiable at a, and you magnify the graph at that point there, centered at p a f of a, it looks like a straight segment. So we've done that, and we've said, all right, okay, here's my graph. I want point P right here, and this is on the x-axis, that's A, right? If you did this, this would be f of A, and we said, okay, if we magnify this, but let's first draw the tangent line. So the tangent line would look something like this, right? That would be my tangent line. And then if I magnify it, okay, we said that here, if I had a point Q, as I move Q closer to A, it will fall along this tangent line right here. So it can be linearized, is what I'm trying to tell you right now, which means I can pretty much, what ends up happening, I don't know why this is messing around with me here. What ends up happening is that it becomes P becomes so close to Q, they're so close to each other that it's pretty much a straight line. Okay, and that was the whole idea of taking the derivatives and finding the tangent line and getting the slope of the tangent, the limit at infinity. Well, this whole idea, this whole process is called linearization when we use it to actually find certain values. If I magnify it so much that this curve right here is pretty much straight at that point, or close to being straight, I can find anything along this tangent line. So I can find values that are really close to point P just by using the tangent line. Okay? Again, let me explain that to you. Since I have a point Q, we'll put that point right here, right? And if I move that Q so close to P, if I move it so close to P, it's going to end up being pretty much straight on this tangent line or close to it. The approximated value will be so close that it's pretty much, the error is negligible. And this also brings up something else called an error analysis. But in any case, how do we do this? How do we make it so close? Well, we know we take the derivative. And we know that we can get a tangent line. Okay, so over here, I'm going to say something is locally linear, and I'm going to create the tangent line. So we have here this equation. Let me highlight it for you guys. And look, it just looks like y equals mx plus b, right? Here is my f of x, and we've got f of x approximately equal to, this is, right, this is y, and this is mx plus b. So what we have here is that equation, and that's going to be our approximate linearization equation of x. And again, here it is in y minus y1 equals mx minus x1 form, right? And that point x1, y1 is, remember, your point P, which is x1, y1, this is really a comma f of a, right? And so that's where I got the, this should just say f, not f prime. That should just say f, not f prime right there. Okay? So that is my a, f of a. All right, so for values close, all we do is linearize this because I am taking a point and moving it so close, let me say it one more time, point Q, and moving it so close, oops, my tangent line I missed, is right there. I'm moving it so close that it's pretty much straight. I've zoomed in so much that it's going to fall along this tangent line. So for anything really, really, really close to P, I don't have to use the actual equation. I can approximate it by just using the tangent line. Again, because I've gone so close, I've straightened it out, I don't need to use the equation to make the calculations. I could just use the tangent line. That's called linearization. All right, so let's move this up, and here it is summed up in this formula, and this is our linearization formula, the linearization of f at a, and you can say that this is our L of x, and here is your f of a plus f prime of a, and again, this is y equals mx plus b. And that's where we get that. All right, so the concept behind linear approximation is very, very, very important to differentials because we know y is f of x. If we take dy, that's f prime of x dx, dy dx is f prime of x. So over here, it lets us, again, by taking the derivative, approximate a lot of values without having to really worry about some abstract function. All right, so let's move on to some applications. Here's the first one. It says, find the linearization of f of x at root x, of f of x equals root x at 1, and then use it to approximate the square root of 1.1. So what is our linearization formula? Okay, we said our linearization formula was, and I'll write it right up here for you guys, L of x is approximately f of a plus f prime of a times x minus a, right? Again, this was y is approximately y1 plus mx minus x1. It was just our point slope formula. We just kind of messed around with it a little bit and put in what our point P, which was a f of a, right, for x1 and y1. Okay, so over here, let's see. I need an a value of 1. Okay, so I have an a value of 1. I can find f of 1. Let's do that first. Plug it into the equation. F of 1 comes out to be 1. Okay, so I've got this. Let me highlight all the things I've got so far as I get them. Okay, I know f of 1 right there. I know my a value is 1. I need f prime of 1 right now. Okay, so let's take the derivative of our function. Over here, I have, I have f of x equaling the square root of x, which is x to the 1/2. So f prime of x will be 1/2 x to the negative 1/2. So that means f prime of 1 will come out to be 1/2. So now I have the next piece of my puzzle. I have this, right? So now I can put all of this in and solve. So this is all part A. Again, I keep picking the wrong item here. Again, this is all part A. So now I can say L of x is approximately, again, I'm saying approximate because it's not exact. We're zooming in so close that it's going to give us a pretty good value because we are so close to that point P. All right, f of a, we know what f of a is. This is f of a right here. F of 1 is 1. So this is going to be 1 plus, okay, so I got that, f prime of a, we did that, that's 1/2, and then x minus 1. So there is my linearization equation, and I'm done with it. Okay, so now for part B, it says use this to approximate the square root of 1.1. Okay, so that means I'm going to say L of 1.1. L of 1.1 comes out to be 1 plus 1/2 of 1.1 minus 1. So this is 1 plus 1/2, all right? This is going to give me 0.1, which is 1/10, right? So 1 plus 1/20th, and that comes out to be 1.05. All right, I want everyone to take out your calculators right now, and I want you to take the square root, this is our function, of 1.1 right here. Here's our function, and I want you to take the square root of 1.1 on your calculators, on calculator. Guess what you get? You get 1.0488. Okay, look at these two values. This is a pretty dang good approximate without having to do anything funky. Again, this is an easy problem, so it may not be applicable to this problem, or maybe here's another situation. If you didn't have a calculator, how do you find the square root of 1.1? Right? If you didn't have a calculator, how do you do that? Well, you can linearize it just like I did here, and you'd easily find the square root of 1.1. Without having to use that calculator. So back in the day, that's why they came up with back in the day, you know, togas and all that. No, just kidding. But back in the day, that's why they came up with these methods, is because they didn't have calculators. So they had to find other ways to approximate these. But the applications continue to go further than that, and we can use it in something called error analysis. But let me do number 2 for you before we talk about error analysis. So here it says, compared delta y and dy for f of x equals x cubed plus x squared minus 2x plus 1 from 2 to 2.05. All right, so this wants us to first find f of, let's get a different color in here so we're not all the same, f of 2. Okay, I plug in f of 2. So I plug it into here, and I will get a value of 9. Okay, I will do the same thing for 2.05. 2.05, I plug it into here, and this f of x equation, and I will get 9.717625. All right, delta y, that means f of 2.05 minus f of 2, and that delta y will give me a value of 0.717625. All right, there's my delta y. Now we want to compare to dy. Well, dy means I need to take a derivative. So I need f prime of x, and in this case, I will get 3x squared plus 2x minus 2. Okay, times my dx, right? All this times my dx. So at f prime of 2, I'm going to say 3 times my 2 squared plus 2 times 2 minus 2. This times my delta x, my dx for this dx will be 0.05. So times 0.05, and I got that by going from 2 to 2.05. That's my change in x. I work this out, and I get 0.7. Now I can compare these two values, and that's the difference between delta y and dy. Okay, we could do the same thing for the next problem, and let's go ahead and, again, I'm going to choose a different color. Let's do this one this time. Okay, so over here, I need f of 2. I got as 9. We already did that. F of 2.01, I could do that, and I will plug it in. I'll get 9.140701. All right, delta y. We know this. We can do the same thing, subtracting, and I'll get 0.140701. Okay, there's my delta y. All right, now let's find dy. dy, I will take the derivative, and I will, which I've done over here, right? And I'll plug in my 2, but this time I'm going to multiply it by 0.01, and I will get an answer of 0.14. Again, you can compare these, where this is the average, this is the change in the two, and this is what the rate of change is going to be. All right, all of this will help us in error analysis. So let's take a look. So again, these are just saying what is delta y, which is a change in y, as opposed to dy, which is that instantaneous that I'm looking for. All right, so over here, let's take a look at this next one for error analysis. This method that we just did above is sometimes complicated or impossible to compute and does have an error to it. So here is how we determine the error. dx is a measurement of error of x, I should say of x, where delta y equals f of x minus f of a, which is the propagated error of y. All right, so we're going to do the example where we're going to find out what this error is. And in this problem it says, the radius of a sphere is measured with an error of 0.04%. Estimate the percent error in volume. So if I know what the error is in my measurement, I could determine what the error will be in the volume. So let's take a look. First of all, let's determine how do we get volume. Well, the volume is 4/3 pi r cubed, right, of a sphere. I'm going to go ahead and I want to know what my dV is, right? Because my dV, this is a change, but an instantaneous. This will give me 4 pi r squared times dr. All right, they gave me the radius has this error to it. So this is a dr over r value, the change in the radius with that error analysis, okay? the radius of the sphere, and that's the percent error. So the change in the radius over the actual radius is 0.04%. Well, what does this mean? This means that if I have my dr over r, this gets sandwiched in between negative 0.0004 and 0.0004. All I did was change that to a decimal, right? So some of you will see a pattern as I do this problem, and that pattern will continue for all of these. But let's just do it the long way, and if any of you see the pattern, that's great. All right, over here, I want my delta V over V, which is my dV over V for this problem, and my dV, I have it. It's right here. It's right in front of me. And I have my V. There's my dV, there's my V. Let's go ahead and write these in. So dV is going to be 4 pi r squared dr all over my V, which is 4/3 pi r cubed. And I'm going to clean this up a little bit. Okay, so the pi's will go away. This 4 will reduce with that. The 3 comes up top. 2 of these r's with one of those. So I get 3 dr over r. This is my dV over V. And guess what I'm going to do with this? I'm going to solve for dr over r. So I end up with 1/3 dV over V equals dr over r, because now I'm going to put this value in here, and that'll give me negative 0.004 less than 1/3 dV over V. Check this out. I went from an error for a radius, and now look at what this value is, an error for a volume, 0.0004. Now I just have to finish this problem out by multiplying everything by 3 to get the dV over V by itself, and that'll give me negative 0.0012 and positive 0.0012. So that means the error in the volume will be 0.12%. So let's try the next one. The next one says, and maybe you'll be able to see the shortcut on this. So the next one says, the side of a square is measured with a possible percentage of 0.5%. So the possible percentage error is 0.5%. So that tells me the side, ds over s, is within 0.05, okay? And this would be a negative on this end. Okay, so that's right away what that tells me. All right, and we know we need to estimate the percent error in the area. We know the area of a square is side squared. So I can say dA equals 2s times ds, right? So if I wanted to get dA over A, I would solve for this, right? And I would plug in these values. That's what I'm looking for, the change in area over area, because here was the change in side over side. So this would be s squared on the bottom, and on the top I'd have 2s ds. This reduces with one of those to give me dA over A equals 2 ds over s. Well, what happens here? That's going to be 1/2 dA over A equals ds over s, and I will put that in here. So negative 0.05 less than 1/2 dA over A, because I just substituted this value in right there, less than 0.05. Now I multiply everything by 2, and I'll get negative 0.1 less than dA over A, less than 0.1. So that means the change in area over area, that error analysis is plus or minus 0.1, which gives me dA over A as plus or minus 10%. And I'll give you a hint what we're doing here. You could take a look, see this 2, see how we multiply, see this 2, see how we multiply, see this 2. Okay, anyway, so that's just a hint on the patterns that you see within these. So I will leave it at that. Hopefully this helped. We were going to do a few more examples in class. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.